Welcome back. In today's lecture, I am going to extend whatever we have learned in the previous class. In previous class, I have discussed about the qualitative behavior of two-dimensional linear system, and either you can tell that qualitative behavior of two-dimensional linear system about the equilibrium point, or you can tell the qualitative behavior of the system. Both are the same in case of linear system. Why I am telling both are the same? Because whenever I have some kind of linear system, in previous class I have considered this kind of linear system, and I am assuming certain kind of initial condition also x0. So either you can talk about the equilibrium point. In order to calculate equilibrium point, we are putting x dot equal to 0, and I am assuming that a matrix, determinant of a matrix is not singular, and due to that reason, without loss of generality, I am assuming x equal to 0 is the equilibrium point. So what happens in case of linear system? Whatever behavior around the equilibrium point, same kind of behavior I can extend everywhere, and due to that reason, either you can talk about qualitative behavior about the equilibrium point or whole system. Both are the same. But if you are going to consider the non-linear system, then this is not true. Why I am telling that is not true? You can see that now what I am going to do, I am going to take little bit generalized system, x dot equal to fx, and I have already told you that whatever analysis I am doing, that is just valid for autonomous system like this, and after that I have again xt0 equal to x0. So here, since I have no linear system, so it is possible to show that due to lack of the additivity and homogeneity property, I cannot tell that whatever behavior around some point, same kind of behavior in the throughout the state space. And due to that reason, whenever we are going to do analysis of any nonlinear system, any kind of theory, then first we specify our reference point. Reference point means those point means we are going to talk about certain point, and one of the obvious point or most important point for the case of nonlinear system, that is equilibrium point. Because why I am telling that is very important point? Because that point has certain property that if you are going to start from that point, and if there is no disturbance, you are going to remain there, and that is equilibrium point. So due to that reason, I am going to talk about qualitative behavior of two-dimensional nonlinear system about the equilibrium point. Okay, anyone has confusion on this point? So whenever you are talking about stability also, please do not tell that some nonlinear system is stable. Emphasis that nonlinear system is stable about certain equilibrium point, unstable about certain equilibrium point. Because in case of pendulum system, you have already seen that one equilibrium point is stable and another is unstable. So if you are going to talk that some pendulum system is stable, then that is meaningless. Due to that reason, you have to concentrate, you have to become specific whenever you are writing papers, whenever you are giving talk somewhere, then please specify that point. Okay, now I think that point become clear to you. Now let us come to the next point. Next point is that I have certain kind of nonlinear system and nonlinear autonomous system. Now what I am going to do, I am going to extend the notion, qualitative notion or phase portrait of linear system to nonlinear system. Okay, so if you see carefully right hand side of this differential equation, then I have something like x, and I have some plot like fx, and I don't know what kind of function this particular function are. Okay, so and this is two-dimensional function, so I have to plot everything in basically, if you see carefully, in three-dimensional plane. Three-dimensional plane means here you can see here, if this is x1, this is x2, then this now replaced by f1, x1, x2. Okay, so suppose I have certain kind of graph. Similarly, I have another graph, and again I have x1, x2, and after that here now I have f2, x1, x2. We are assuming that f function f is represented like f1 and f2, like that. Okay, so what happens? It is possible to show that one can approximate any continuously differentiable function, okay, or one can represent any continuous differentiable function in some other coordinate frame. Here you can see that coordinate frame is x1, x2 we are telling, or f1 you can tell that using three-dimensional coordinate frame we are representing the graph between x1, x2 and fx1, x2. So for simplicity, just you can start from those kind of function which has only one independent variable. Okay, so what I am telling, okay, now I am going to consider little bit simpler function where I have this, you can take t and this as a ft. In order to avoid confusion, I haven't write here x or fx, okay, because fx I am assuming that is vector quantity. So what I am going to assume here, suppose this is t, a scalar, and ft is also one dimensional function. So I have some kind of one dimensional function, and you can see that using some plane I can represent this function. And whenever we are writing function, so function may have different characteristic. They might like this, any other shape. Okay, it is possible to show that this function, same function, can be represented in another coordinate frame. Okay, and that coordinate frame is framework of polynomial. And I hope that you all are already aware about what is meaning of polynomial. So whenever I am writing some kind of polynomial, so I am writing like a0, after that a0 t, after that a1 t, sorry, and after that a2 t square, something like that. We are writing like this. Okay, so this is some kind of polynomial way of representing some function f dash, you can write. So like this. So what is main idea, that initially I have coordinate system like t and ft. Now I am going to represent any continuously differentiable function in terms of some polynomial coordinate system. Polynomial, why I am telling coordinate, you are able to understand now that whenever we are talking about any coordinate system, at that time what basically we are doing, suppose that I want to represent two-dimensional plane. So we are going to select the independent vectors. Okay, so in this two-dimensional plane, we have independent vector like 1 0 and 0 1, and it is possible to show that if I know these two independent vector, so scaling this independent vector by c1 or x1 you can write, then things become little more clear. Suppose if I multiply with x and after that I will do linear combination, then you can see that you are able to generate any point in this particular space. In this whole space, just by scaling x and y, you are able to travel in this whole two-dimensional plane. Okay, so these two are called bases. And what is property of basis? That these two are independent vectors, and how basically we are checking some two vectors are independent. We are multiplying with alpha 1 to that vector and alpha 2 with another vector, and after that we are checking the solution. If solution of this is alpha 1 0 and alpha 2 0, then we are telling that these two vectors are linearly independent. Okay, another thing we are concentrating, that suppose I have three basis vectors. So one thing that we are checking linearly independent, another thing we are checking that using these two vectors I can able to span whole space or not. If we are able to do two things, that spanning the whole space and all vectors inside whatever vector I have selected that is linearly independent, then we are giving some specific name that is called basis. So that is called basis vector, and basis vector is somehow also denote the coordinate system. Okay, and these points are called coordinate. So in order to represent some point, we are scaling this coordinate system. Coordinate system here I have taken two-dimensional, so coordinate system is x and y, but here basically that is the coordinate point of some the coordinate of some point basically. And this whole axis I am interpreting as a 1 0, this whole axis I am interpreting as a 0. Okay, so basis whenever we are talking, then at that time we are talking about a span. A span means I can able to travel in whole space, and after that we are also talking about independent vector, linearly independent. Okay, now let us try to see that whatever coordinate frame now I am going to select, and I am telling that now I am going to represent any function. So polynomial is also one kind of function using some kind of simple function, and sorry, that simple function is nothing but some kind of polynomial function. So suppose that just you can take some kind of quadratic polynomial for simplicity. So if I will take like this a1t and after that a square t square like this, it is possible to show that now here my basis is 1t or t square, like that I have something like this. Okay, so any quadratic polynomial, if you know 1t square, so just now and these point are just give the coordinate of that particular polynomial. So if you vary a0, a1 and a2, then any polynomial, and whenever we are representing polynomial at that time we are using this notion. So 2, so p2 we are also writing this has a p2. Okay, now if you check individual, then individual represents some kind of basis, because you can see that if I know these three, then any two-dimensional any quadratic polynomial I can trace by varying a0, a1 and a2. Anyone has confusion on this? Okay, after that just I have to check that this is linearly independent or not. So you can see that alpha 1 plus alpha 2 t and alpha t square, and that equal to 0. 0 means I have 0 plus 0t plus 0t square. You can see that solution is alpha equal to 0, alpha 2 equal to 0 and alpha 3 equal to 0. And due to that reason I am telling that these three are linearly independent quantity, so qualify for the basis. Okay, and able to span the space. So idea is that suppose I have some kind of function, continuously differentiable function. We will see that why continuously differentiable function. It is possible to show that at some point, because I am not telling that using single polynomial you are able to represent the whole function. Okay, but it is possible to show that in neighborhood of some point, okay, you have some kind of coordinate frame like a0, a1 and a2, and basis remains the same. So using infinite dimensional basis, why I am telling infinite dimensional, here you can see that a0 t, a2 t square, a2 t cube, and this is up to infinity. I don't care where this is going. So my coordinate system is, in order to represent something, I have taken infinite dimensional coordinate system. Okay, so and in that particular coordinate system I am going to represent some function, and you can see that whenever we are talking about equilibrium point, so I am talking about some point. So basically I am just going to concentrate in some vicinity of that particular equilibrium point. So I am going to represent that particular function in that particular vicinity. So that is the idea. Anyone has confusion on this, then please let me know. Anyone? So basically game is like this. You have any function, but their representation is very complicated. It might possible sin theta, cos theta, combination of that, x square, x cube, I don't care. Okay, now what I am telling, that particular function can be represented by simple function, that is polynomial function. Okay, and now I have question is that how to find this A0, A1 and A2 in this particular neighborhood. So let us come to the idea, and basically this idea that any regular you can tell, regular means I am taking some kind of regularity, means continuity here I am taking, that continuously differentiable function I have considered. So this idea is basically coined by the Taylor series, and you might have seen that several places I have different use of Taylor series, and particularly it is possible to show that if you have some kind of nonlinear system, and if right hand side of nonlinear differential equation has certain property, then about some point, particularly equilibrium point we are taking, and I will tell you what is the reason to take equilibrium point, then I can approximate nonlinear system like some kind of linear system. And we know that how to define nodal point, saddle point, centers in case of the linear system. So I am going to use that kind of theory, but main idea you have to understand that how basically that approximation comes into picture. So approximation comes into picture like this. I have initially some function, because right hand side of differential equation is somehow some kind of function. So what I am telling, that whenever I have some kind of nonlinear system, then right hand side of that differential equation is somehow some kind of function, some kind of multi variable or multi real valued function. That is, now what I am going to do, I am going to approximate that particular function about some point using some kind of polynomial function. Okay, and dimension of polynomial might be infinity also. So very high dimensional polynomial, using very high dimensional polynomial, I am going to first represent that, and after that I will truncate based on our requirement. So let us try to see that. Now question is that, so up to here everything is fantastic. That idea is that you have function some ft. Now I am claiming that okay, I can represent this function, any function, in form of some kind of polynomial. Okay, so like that, like this. But question is that how to calculate a1, a0, a1 and a2. So you can see that this is some kind of, if you see in terms of the equation, so I have some kind of algebraic equation, and that is one algebraic equation, but infinite number of variables are involved here. Now question is that how to calculate that variable a0, a1 and a2. Okay, now one of the way to calculate that I am going to illustrate here, you can take one polynomial, and here maximum order of this polynomial I have taken 3. Okay, so you can also write this as a p3, this polynomial as a p3. Now you can see that if I shift this polynomial, so I have some kind of polynomial, and after that I am going to shift that polynomial by minus c. So you might have seen that if you have some graph and you are going to shift minus c, then what happens, that positive increment comes into picture. Anyone has confusion on this? Okay, shifting of graph you might have learned during your school time. So due to that reason, we are telling that this function x is shifted by c. So if you shift this, then this polynomial will generate new polynomial. I am not writing equality sign, just I am shifting the polynomial. So this is my shifted polynomial. After that, what you can do, now you can open this. So I have x plus c, x square plus 2c plus c square, and x plus c power whole cube. And if you simplify this, it is possible to show that I have, and after that just you can rearrange the term. So after rearranging, you can see that again this remains the same. This particular basis, you can tell basis remains the same, just coefficient is going to change. Okay, because shifting the polynomial, I am not going to lose the space, so I am going to remain in the same space, just coefficient or coordinate is going to change. Okay, now you can see that whatever coordinate that comes into picture, that is again a polynomial. So I have defined that polynomial as a PC. Okay, so I have shifted to C, and by by putting C, I can able to understand what is A0, A1C, A2C and A3C. Okay, now if you see next one, then what happens by differentiating this, you are able to generate next one means coefficient of x. If you further differentiate it, then you can see that I am going to generate, and dividing by factorial 2, I am going to generate the coefficient of this. Similarly, if you differentiate this, then you are able to generate this. And due to that reason, what happens that I have some concrete result, and what we are telling that the coefficient of translation of polynomial by minus c involve the derivative of pc. So what kind of beautiful property here comes into picture? You can see that till now I have just talked about linear algebra. Linear algebra means I have some kind of function, I am defining some other coordinate frame, and whatever coordinate frame I have selected, that is based on some kind of polynomial. So I am telling that I have some kind of infinite dimensional basis, and based on that I am going to represent some function. And after that, when I have shifted that particular coordinate system or polynomial, then what I found that whatever coefficient, that their derivative automatically comes into picture. So this is somehow tell us that how to go from algebra to calculus. You can see that whenever derivative comes into picture, then notion of calculus comes into picture, and due to that reason, calculus is not away from the algebra. Okay, it is possible to show that calculus is not a new subject, that is extension of algebra only. Okay, we will see that point whenever we have time. Okay, now what I am telling now, that suppose I have some polynomial and I have to tell that what is meaning of derivative of polynomial, and during your 10 plus 2 you have already learned about this, so I am not going to repeat, because here a0 that is constant, so derivative of this is equal to 0, and whenever I am writing p dash, it means that I am talking about dp by dx, whatever independent variable, so I am going to take derivative about that, and after that I have this kind of things. So this I have represented by dp. After that, what I am telling that if I have some kind of polynomial like this, and if you shift that polynomial, then I will generate like this. Okay, so just proof of this you can able to do by induction also, but here I have just skipped the proof. Okay, so what I am telling that for all c, you can take whatever increment you want, you can take that increment, and after that what we found that if you will take this increment, then pc p dot p derivative c, p double derivative c by factorial 2, and this kind of things comes into picture. So, and after that what I am going to do now, you can see that I am going to replace x by x minus c, because I have to see the approximation of this particular function. So I have some kind of polynomial function, and I want to approximate this polynomial about some vicinity, and that vicinity is nothing but c. Okay, so I am going to approximate that polynomial about the c. So what I am going to do now, but this polynomial is basically different. You can see that here px plus c after shifting the polynomial. So now from this expression I want to come to my original polynomial. So one of the simple way what you can do, since this is function, so replacing argument of function everywhere, that is property will not going to change. So same property I am going to apply here. So I am going to replace x by x minus c. So if you replace x by x minus c, so here if you substitute x minus c, so you can see that c and c is going to cancel out, and after that whatever things that comes into picture, that is nothing but nice Taylor series expansion comes into picture. Anyone has confusion about this derivation, then please let me know. So just by doing shifting and involving some property of calculus, I am able to generate the Taylor series. Okay, so basically what happens that what is our main idea, that suppose in some vicinity I have some polynomial, so if you shift that polynomial by some small amount, then somehow regularity remains the same, so symmetry remains the same. So if you shift that, so from there you are able to get some kind of information. So using that information I have basically derived this kind of expression. Anyone has confusion till now? Okay, if you don't have confusion, then I will tell you the different picture. Suppose that if you don't like this way, and what you are going to see now, that you are going to see different way to generate the coefficient of the polynomial. So what you can do here, suppose I have some kind of fx, and what I am telling that fx in vicinity of some points c I am going to represent like a0, and suppose without loss of generality I am taking c equal to 0 because equilibrium point is 0, I am assuming for time being. So you can see here that I can represent like a1x, a2x square and up to infinity. Now I have to calculate a0, a1 and a2, and what we are telling that if I have some kind of function, so here I have, suppose I am going to take some kind of function like this. So this function you can see that is passed through the 0. Some function might not be passed through 0. So what basically we are telling that whenever you have to approximate at x equal to 0, first you try to approximate with constant function. So due to that reason, forget about all other term and see that fx first I am trying to approximate with using some kind of constant function. Second, if that is not approximated perfectly, you can see that if you draw real line and if function is like this, then I cannot approximate it, and due to that reason I am going to some kind of more dimension. I am going to add one more dimension, and I have added some kind of linear function. After that, even if that is not, then I will add some kind of quadratic function or parabolic function, and similarly I am increasing the order. That is the physical interpretation. Okay, now since you are going to do approximate everything nearby of this, so you have to see some kind of local operator to generate how to generate a0, a1 and a2. So for that, what I am going to do, first I am going to substitute that point. So I have done approximation about x equal to 0. So first you can substitute x equal to 0. So you can see that in this way I can generate what is a0, because by substituting x equal to 0, what happens, everything, all other thing become 0. Now since I have just one equation and I have to know a1, so what, and you are going to approximate nearby of this, so try to select those kind of operator which is just talking about the some kind of property in some neighborhood, and that kind of operator is differential operator. So you can differentiate this with respect to x. So if you differentiate this with x, you can see here that a0 is constant, so due to that reason 0, and now I have a2x, and like this. Now what you can do, you can again substitute x equal to 0. So if you substitute x equal to 0, then automatically all higher order term equal to 0, because that is multiplication of x, and in this way you are able to generate or know what is a1. Okay, now if you want to generate a2, then what you can do, you can take one more time differentiation of same function with respect to x, and after that you can substitute x equal to 0. So you can see that now a is constant and here x, so 2ax, 2a2x, and after that all higher term, that is multiplied by some kind of x. So x is everywhere involved. So if you are going to put, then this equal to 0. So you can see that automatically I can able to know a2 is nothing but double differentiation of this and divided by 2. Okay, so if you check higher third term, that a3, then you can see that this again become constant, and after that I have 3 multiplied by 2. So due to that reason 1 by factorial 3 comes into picture. So in this way also there is no need to remember Taylor series. Okay, so if you have idea of basis, if you have idea of local operator, then also you are able to generate the Taylor series. So please do not remember the Taylor series. Up to here anyone has confusion? Then please let me know. Baby Dana?
Yes, sir.
Any confusion?
No, sir. No, sir.
So are you able to visualize what information I am going to share? Most
Yes, sir.
of time what I found that students are remembering the Taylor series and they become very much frustrated when they are not able to recover. But what we found that there is no need to remember anything. Okay, now let us come to the dynamical system. Okay, so I have now explicitly mentioned that qualitative behavior near the equilibrium point. Okay, so I am not talking about the qualitative behavior of whole dynamical system, just I am going to concentrate about the equilibrium point. Okay, so here you can see that I have this two-dimensional nonlinear system, and I am assuming that P1 and P2 is the equilibrium point. So how to confirm P1 and P2 is the equilibrium point? If you are going to substitute P1 P2, then that becomes 0. Similarly, if P1 and P2 is the equilibrium point, so these two equations should be satisfied. So here this is AND operator. Okay, so whenever you are writing AND operator, then most of time we are writing like this. This is AND operator. Okay, so if you solve these two algebraic equations, then you are telling that what is your P1 and P2, that is the equilibrium point. Okay, now what I am going to do, I am going to apply Taylor series. So here initially what we have seen here, that if I have just one variable, then the Taylor series is given like this. Suppose if I have two variables, then I have a0, a1 x, and with respect to first variable, and after that I have a2 x minus p2 with respect to second variable, and similar kind of things is going to continue till higher order. Okay, so I am not going to give the explicit expression for that. Just you can see that I have some function, and in order to approximate that function about p1 and p2, so I am assuming that in two-dimensional plane I have some point, this is p1 and p2, that is equilibrium point, and I am going to approximate system about this particular equilibrium point. So I am going to substitute that point, and after that I have some constant, and here increment x1 minus p1. After that a1 to another constant, and here another variable x2 minus p2, and I am going to collect all higher order term. Okay, and similarly similar kind of things I have done for the second equation, and after that higher order term. You try to see here that if you are very close to the equilibrium point, then what happens, that x minus p1, that is very less. So this quantity is very less, and obviously this quantity is also less. So if you are consider the higher order term means x1 minus p square. So x1 minus p square is basically lesser than x1 minus p, because we are very close to the p1 point, and if you are very close, it means that your whatever your distance, that is less than 0. So if that is less than 1, so if that is less than 1, so what happens, if you are going to consider, suppose that distance you can take 0.025, and after that you can do the square of that, but you found that this quantity is further less. So higher order term is very less, and due to that reason, what people are suggesting that if you are very close to the equilibrium point, then one can neglect this higher order term. Okay, and basically idea of feedback linearization is idea of linearization, not feedback linearization, is basically motivated by this only, and due to that reason you can see that since I am neglecting the higher order term, due to that reason whatever linearization technique, that is only valid about this equilibrium point. Okay, very near to the equilibrium point. Here I have already assumed that P1 and P2 is the equilibrium point, so this point is 0 and this is 0. Anyone has confusion on this? Why I am going to take this as a 0? Because P1 and P2 is the equilibrium point. Okay, now what I am going to do, I am going to define some new coordinate frame, and this new coordinate frame I have defined y1 equal to x1 minus p1, and this is definition y2 equal to x2 minus p2. Here for the simplicity I am assuming that this is some kind of constant. Okay, so if that is constant, and if you will take the derivative, then you can see that y1 dot equal to x1 dot, and x1 dot you know from here, that is a11 x1 minus p, and after that a12 x2 minus p, because this is already 0. So and after that what I am going to do, I am going to that collect all term here inside this matrix A, and right hand side you can see here that I have x1 minus p and x2 minus p. So basically this y is some kind of vector that contain x1 minus p1 and x2 minus p2. Okay, and if you substitute here at this point, so you are able to see that A matrix is nothing but a11, a11, a12, a21 and a22. Now in order to calculate a11, you can use the same idea. You can take the first derivative with respect to that variable. So dou f by dou, suppose if you have two variables, then you can take with respect to x1, and due to that reason you can see that I have written like this dou f1, because in this a11 I have this function is involved, just f1 function is involved here, f1 x1 x2 this function is involved. So I am going to take partial derivative of this with respect to x1, then that will generate a11. After that partial derivative of f1 with respect to x2, then that generate a12, and due to that reason I have written here like this. So anyone has confusion why df1 df1 same thing is coming here? If you have confusion, then please let me know. Okay, and after that similarly here I have to do same kind of things, and I have to calculate this matrix, okay, at certain point x1 equal to p and x2 equal to p2, because I am telling that whatever linearization I am going to do, that is valid near of this. So if you substitute this point here, then you are able to generate some kind of constant matrix. So now nonlinear system is converted into some kind of linear system about some point. Now you are able to understand why I am telling that functions should be continuously differentiable in all argument. You can see that if that is not continuously differentiable at some argument, then what happens, I cannot able to calculate this, and Taylor series expansion become fail. So if you have some kind of system where differentiation with respect to some variable is not possible, then you can not able to linearize that system about that point. Okay, and I will give you some example in tutorial that why sometime people are doing blend linearization, and after that what happens, that if that is not differentiable, then some problem comes into picture. Okay, so linearization technique is very restrictive. They are telling that I can able to do linearization only something is differentiable. Okay, and if you see the original system, then most of time right hand side of differential equation might be not differentiable due to some external factor, due to some, there are several internal perturbation that is going to disturb the differentiability of some function. So at that time I cannot apply this kind of linearization technique. Another restriction, that linearization technique is only valid about the equilibrium point. I do not know up to what extent that is valid. Okay, because we are telling that some sufficient vicinity of equilibrium point. So how much sufficiently close we are, I cannot quantitative way I cannot picture out, and due to that reason I do not know up to what range this linearization technique will work, and due to that reason most of time nonlinear control community is suggesting that whatever linearization technique that is very restrictive. So whenever you are using that, please try to make or operate your system very close to the equilibrium point. If you deviate little bit, then you are not able to understand what is the property of the resultant system. Okay, now let us come to the one simple example. So I have taken the example of pendulum system, and I hope that you have already seen this example, and so I am not going to drive again the differential equation. You can see here that I have basically x1 dot equal to x2, so I have written fx here, that is x1 x2. Okay, so whenever you are writing f1x, it means that here f1 contain some kind of function which map from R2 to R. Anyone has confusion on this? Because I have two variable x1 and x2, and due to that T mapping from R2 to R. Okay, similarly, similar kind of things here. Now we are already seen that this is the equilibrium point. So I have two set of equilibrium point whenever we are talking about the pendulum. One equilibrium point that is below this, and after that one equilibrium point that is above this. So we are going to see or analyze these two equilibrium point based on the theory of phase plane analysis. So what we have to do, first I have to linearize the system about the equilibrium point. Okay, so if you linearize this, so here dou f by dou x, and that is nothing but dou f1 by dou x1, dou f1 by dou x2, dou f2 by dou x1, and dou f2 by dou x2. So this is also called Jacobian matrix. Okay, and when we will read the linear transformation, at that time I will tell you some another interpretation. Okay, that suppose that whenever we are in two dimension, suppose that if I have some function, so we are interpreting that suppose I have here, so differentiation of this is nothing but tangent to this. Okay, suppose you are in higher dimensional plane, then how to give the physical interpretation of that, and it is possible to show that using Jacobian. Okay, and Jacobian I am going to interpret using some kind of theory from abstract or linear algebra, and after that I will tell you the physical interpretation of the derivative in higher dimensional plane. Okay, when I will deal with the linear algebra. Okay, so just for intuition, that if you are just one variable, then comfortably you can interpret that if I have derivative at this point, then geometrically there is nothing but tangent. Okay, but you can see that if you are in three-dimensional space, some three-dimensional space, then it is very difficult to realize the tangent. Why difficult? Because you can see here that if you are at certain point, then from one point infinite many plane will pass through that. Okay, and what is the derivative, you have to interpret precisely, and using Jacobian one can interpret that. Okay, now here this is the linearization, and after that what I am going to do now, I am going to check the linearization about two set of different equilibrium points. So just you can take one equilibrium point, that is 0 0. So if you substitute 0 0 here, so you can see that after substituting 0 0, I can able to get here 0 0 0 and 1. This is already constant, so cos x1, so whatever my cos x1, so I'm going to change the color because this is not visible. So here this, so I'm going to substitute here x1 equal to 0 and x2 equal to 0. I'm going to substitute. So if you are going to substitute here, since x2 variable is not involved here, so cos x1 is nothing but -1. And now what you can do, you can just check the eigenvalue, because in previous class what we have seen that in order to do phase plane analysis, just I have to check the eigenvalue, and if I check the eigenvalue, then eigenvalue is complex. And we have already seen that in case of complex eigenvalue, basically I have three different kind of behavior. Either I am going to converge, I am going to diverge, or I have some kind of center. Okay, so either I am going to diverge, I am going to converge, or going to remain in some specific orbit. And in previous class, what we found that if alpha that is greater than 0, means real part of eigenvalue greater than 0, then I have unstable focus. Okay, if that is alpha less than 0, then I have a stable focus, and this I have interpreted as a center. Okay, so let us see here that alpha is negative, and due to that region that is a stable focus, it means that if I start in the vicinity of the equilibrium point, so I have pendulum, and if I operate pendulum in vicinity of this, then what happens that if you perturb this pendulum at this point, and if you leave it, then automatically they will come to their equilibrium point. Anyone has confusion on this? Okay, now suppose that I am going to linearize about the topmost point. Okay, so if you do linearization about the topmost point, then what happens? You can substitute n equal to 1. So if you will substitute n equal to 1, at that time what happens? By substituting n equal to 1, I have pi and 0. So if you substitute pi and 0, then you can see there now matrix is going to change. So linearization about topmost point, and now topmost point is x1 pi and x2 0. You can see that now I have this kind of matrix. Okay, and if you calculate the eigenvalue, then I have two eigenvalues. So one eigenvalue is negative, another one is positive. Okay, so one eigenvalue is negative, another one is positive. Rajesh, could you please tell me that what is the behavior? Rajesh, are you here?
Hello, sir.
So suppose that I have two-dimensional linear system and one eigenvalue is negative and another one is positive. Then what is behavior of the equilibrium point or system? You can tell linear system.
Diverging.
What?
Diverging.
Yeah, diverging, but we have given some specific name that is called saddle point.
Saddle point, sir.
If you might have seen this kind of behavior, no,
Yes, sir.
in previous
Yes,
class.
sir.
Okay, so this is basically saddle point. Okay, so what happens? That try to see what is meaning of saddle point in the practical case. So I have pendulum. Okay, so you can see here that if you perturb pendulum by some small amount, then what happens? That pendulum is going to, suppose that perturbation is too strong, then you can see that again they trying to converge towards this equilibrium point, but due to perturbation they can again not maintain it. So in this direction they are diverging, and if you look from this side, if observer in this side, they are converging. So similar kind of behavior, but finally I will diverge. Okay, so similar kind of interpretation is coming from mathematics also. Okay, up to here anyone has confusion? Okay, if you don't have confusion, then now I am going to make very important remark. Okay, what is remark? Suppose that if you linearize your system about the equilibrium point, okay, so automatically you will get the linear system. After that, suppose that whatever eigenvalue of the linearized system A, and if that is a stable node or nodal, if that might be some kind of stable focus, or what is another possibility? Anyone? So what we found, that if both eigenvalue is negative, then I have a stable node. If both eigenvalue are complex, and if alpha less than 0, then I have a stable node. You can see here in this case what happens, that corresponding nonlinear system. Okay, I am going to talk about the property of nonlinear system by seeing the linear system. We are telling that corresponding nonlinear system become stable about that particular point if I have some kind of linearized system which has a stable node and a stable focus. Okay, if eigenvalue of A, that is unstable node or unstable focus, okay, and or saddle, okay, in these three cases what happens, that corresponding nonlinear system. So I have, suppose I have some kind of nonlinear system which trajectory is like this, and after that I am going to view that trajectory using some kind of linear scope, and in linear scope I have used the idea of eigenvalue, and what I found, that eigenvalue is unstable node, unstable or unstable focus, or unstable saddle. Then I can comment that this particular nonlinear system is unstable about that point. Okay, so in this way I can able to comment the stability of nonlinear system just by seeing the linear system, but I can only able to comment the stability in this particular neighborhood. Okay, I cannot able to talk stability everywhere. I am only able to talk stability about the linearizing point. Okay, you can see that here I have covered almost all case: stable node, stable focus, unstable node, unstable focus, and saddle point. Could you please tell me that what happens if real part, okay, if I have real part of eigenvalue that is equal to 0, so I have purely complex or purely imaginary eigenvalue, then what one can conclude? System corresponding nonlinear system is stable or unstable. What do you think, Sunidhi?
Sir, oscillatory response with imaginary.
So original linear system is oscillatory. Okay, so oscillatory things is also one can interpret as a stability, because what stability people are defining, that you have to maintain, okay, your future trajectory in neighborhood of equilibrium point. In that way, basically we are talking about stability, that bounded input give us bounded output, like that, something like that. Okay, so what do you think? Suppose linear system is oscillatory, then non-linear system is also oscillatory.
Uh,
So from this intuition, it looks like that. Okay, but that is not the true. I will tell you the story why that is not true. So let us try to see that if equilibrium point is center, what does it mean? That after linearization, whatever matrix that comes into picture and their eigenvalue is purely imaginary, then try to see the case. What happens? Suppose the eigenvalue of, suppose the linear system x dot equal to ax, and what I am assuming that here eigenvalue of a, that is purely imaginary, so plus minus j into beta, and here I am defining j as a square root of minus 1. So in this case, what we found, that in two-dimensional plane x1 and x2, that I have some kind of center kind of behavior. Center means also you can interpret that if I am going to remain in this axis, then I am going to continue in this particular orbit only, not axis, orbit I am telling. Okay, now what happens, that suppose some perturbation comes into picture, because what, how basically we are applying linear and non-linear control theory, we have some system, and after that we are doing mathematical model, and inside a, if you check the a matrix, then system parameter is going to appear. Okay, so suppose you can just take a very simple system. This system I'm going to take, I have applied some force ft, and after that I'm going to note the position, and after that if I apply, suppose the Newton's law dt, and after that I will get this ft. Here you can, if you represent this in a state space form, then automatically you are able to see that this mass matrix, okay, is going to reflect somewhere. Okay, suppose that, yeah, I have applied some kind of force that is function of x, means I have applied some kind of feedback, because here I am not talking about force system. So I have already told you that you can design the feedback. So suppose I have designed feedback like this, ft equal to k multiplied by x. You can see here that m and k, these kind of quantity comes into picture, and it is possible to know precisely, you can not able to measure anything. So what happens, automatically some perturbation comes into picture. Okay, now try to see the case when you have purely imaginary eigenvalue. So whenever I have imaginary eigenvalue, at that time I have this kind of structure. So what does it mean? That if I have purely imaginary eigenvalue, at that time these two quantity, alpha equal to 0 at both place, so I have beta and beta. Okay, suppose that if I will consider eigenvalue of a is plus minus I, plus minus j, so it means due to that reason I have retained 1 and minus 1. Anyone has confusion? Or you can write minus 1 here and plus 1 here, that doesn't matter. Okay, anyone has confusion on this? Now it might possible if I have very small perturbation. So I have represented that perturbation by mu. Now let us try to check the eigenvalue of this. So mu, you can take any small value of mu. Then what happens if you check the eigenvalue of this particular matrix? So if mu is greater than 0, it is possible to show that is converted into unstable focus. So initially, if mu is purely imaginary, then I have some kind of center kind of behavior or some kind of orbit kind of behavior. Okay, but if this matrix is perturbed by very small amount, then what happens? Two parameters mu and mu, here also it might possible some parameter is going to reflect, but for simplicity I am assuming that there is no perturbation here, some small perturbation here. Now please check by yourself that if mu greater than 0, then it is possible to show that I have one eigenvalue, okay, or I am talking about unstable focus. It means that complex number, complex part of real means I have some kind of eigenvalue that is in form of complex number. So this part is either positive or negative. So if that is positive, then I have unstable focus. If that is negative, then I have a stable focus. So what happens? I cannot able to tell correctly that what kind of behavior comes into picture. And whenever we are linearizing some nonlinear system about that vicinity, it might possible perturbation sometimes fall in this direction and this direction. I don't know. And due to that reason, I cannot able to tell that precisely what kind of behavior comes into picture. A stable focus or unstable focus. And due to that reason, linearization technique is going to fail if linearized system has some kind of eigenvalue that is purely imaginary. Anyone has confusion on this point? Have you understood the interpretation or not? What I am telling that in order to generate center kind of behavior, I have to precisely put eigenvalue at imaginary axis. But due to some calculation and due to some kind of error, precisely I cannot put on imaginary axis. Then what happens? Either that will come on the left hand side of imaginary axis or right hand side of imaginary axis. And due to that reason, what happens? That I have either unstable focus or a stable focus, and so I have some kind of contradiction. So sometimes I do not know what is the behavior, and due to that reason, whenever after linearization about the equilibrium point, if you have purely imaginary eigenvalue, then we are telling that linearization technique about the equilibrium point is no longer applicable. Anyone has confusion? It means that I cannot comment stability of nonlinear system. So in that particular case, linearization technique will also fail. Okay, so let us try to check some example. So what I am going to do, that I am going to take one example, and before that I am going to give definition, then I will come to the example. So phase portrait of the center may not persist under perturbation. It means that sometimes stable and unstable, and due to that reason I cannot comment stability about the equilibrium point of the corresponding nonlinear system. So what is meaning of hyperbolic equilibrium point? The equilibrium point is called hyperbolic if A has no eigenvalue with zero real part. Okay, it means that in order to talk about the stability of the linearized system or stability using linearization, I have to just consider this class of system only. And this class of system is called hyperbolic system, means or hyperbolic equilibrium point, where after linearization real part of eigenvalue is not equal to 0. Okay, so if I have hyperbolic equilibrium point, then only I can talk about the stability and instability of corresponding equilibrium point. And I have taken this very simple example, and if you linearize this about the origin, it is possible to show that one of the way to linearize by intuition also, what you can do, you can avoid the all higher order term, and you can see that now my system is x1 dot equal to minus x2. So you have something like this 1 and 0, and if you calculate the eigenvalue, you can see that that is purely imaginary. So I can, after linearization, I cannot see the not able to talk about the behavior of this system. And in next class I will tell you that one very beautiful behavior that is called limit cycle that comes into picture. Okay, and how to construct some kind of oscillator that is stable. Up to here, anyone has confusion? Then please let me know. Up to here, anyone has confusion? Taslima,
No, sir.
Ruchi.
No, sir.
Okay, now I am going to close this class. Just I will give you another intuition. Okay, this is one of the way of linearization. But what happens in control theory, whenever you are going to write the paper, at that time you have to write everything in very concrete way, and it is possible to show that linearization one can also do based on mean value theorem. Okay, so quickly I will within 5 minutes I will going to complete it. So what basically I hope that you are already aware about mean value theorem in calculus. If you don't aware, then please go and check it. But I am also going to give you the overview. So in order to, but here what is difficulty I have, whenever we are talking about calculus or 10 plus 2 calculus, at that time most of time whatever function I am going to talk, that has only one independent variable. But here I have several independent variable, at least two we consider whenever we are going to talk about the linearization. Okay, because I am going to talk about the nonlinear system, and I am going to talk about some kind of system x dot equal to fx, and here I am assuming x belongs to Rn. Okay, so first I have to define something, and after that I can apply the classical mean value theorem. Okay, so suppose I have n dimensional space, because this system is defined in n dimensional space, and now what I am going to do, I am going to select 2 points, point x and y are two distinct points in Rn space, and so I am in Rn space, means higher dimensional space, and I want to draw some kind of line in this space, and I have defined that line is Lxy, this point is x and this point is y. So one can define line like this. Okay, so this is very general definition of line, and here you can see that whenever we are defining the line, at that time we are using the convexity property. Okay, so theta x and 1 minus theta x and theta lie between 0 to 1. So in this way we are defining line in higher dimensional plane. Okay, now after that let us come to the mean value theorem. So what mean value theorem is telling, suppose you have some kind of function which mapping from Rn to R. So you might have seen that suppose I have two dimensional system I am taking, and after that x2 dot equal to f2, x1 and x2. So could you please tell me that what is mapping of this particular function f1, x1, x2? Anyone? Rajesh, could you please tell me the mapping of this function f1, x1, x2? So Rajesh, are you here? Sunidhi,
Sir, R to R.
R2 to R. So similar kind of, suppose even if I have n, so this kind of mapping comes into picture. Okay, and what I am assuming that whatever function f that is continuously differentiable at each point in open set. Do not worry here why I have written open set. I will tell you about that story in the next part of this course. Just for time being, you can tell that open set means boundary point is not included, we are assuming. After that, let x and y be 2 points of S such that line segment, we are assuming that whatever line segment that is going to lie in that set, it is possible to show that if there is point on Z, so this kind of property comes into picture. So I can able to establish the relation. So I have some kind of line x and y, and this line is Lxy, and suppose I have some kind of point Z. So I can able to show that Fy minus fx by y minus x. So basically this is nothing but derivative. So derivative of some point x equal to z. Okay, so this is the mean value theorem. Okay, and interpretation, these kind of things, please just check it because that is a straightforward. Now what I am going to do, I am going to just write the multi-dimensional version of this. And what is multi-dimensional version? You can see here I have changed the mapping from Rn to Rn, and this is called multi-dimensional version of the mean value theorem. And at that time you can see that everything remains the same, fy minus fx, and after that y minus x I have, but I have something comes into picture that like this. So initially in one dimension just I have dou f by dou x, but generalization whenever we are mapping from Rn to Rn, okay, at that time I can able to write like this. Okay, so now let us try to see that here how basically this kind of things comes into picture. Whatever, why I have able to write like this. Okay, so I have defined the Jacobian matrix Jx. I have already told you that how to define Jacobian. This is matrix. Why that is matrix? Because dou f1 by dou x1, dou f1 by dou x2, and like this. Similarly here, dou fn by dou x1, like that. So I have some kind of n cross n matrix if I have n dimensional things, and I have represented that matrix like this. Okay, and this is x. So in this way we are defining the Jacobian, and after that what I am going to do, I am going to take another function h sigma, and I have defined h sigma like this, fx sigma y minus x. Okay, and you can see that if sigma equal to 0, sigma is included here, then this will gives us the sigma equal to 0 fx. When sigma equal to 1, then you can just substitute here, so that is 1. It means that this function, suppose you are here and you are here, so by varying sigma you are able to move from this whole line segment in n dimensional plane. That is the meaning. Whatever function I can able to generate each function from here to here by defining like this. Anyone has confusion on this? Just by changing sigma I can able to travel from this point to this point, and this is true because we are talking about convexity. Okay, now what I am going to do, I am going to do the apply the chain rule. So if you apply chain rule, so I am going to take derivative of this h with respect to sigma. So dou h by dou sigma I am going to do. So if you take the derivative, then here dou f by dou x comes into picture. Okay, so dou f by dou x, and after that dou f by dou sigma, sorry, so dou f by dou sigma, and after that I have dou whatever this quantity. So I have to calculate dou f by dou sigma. So I can write dou f by dou x, and after that I can able to write that since somehow I have to write dou x by dou sigma. So basically what I am telling that I have to differentiate this, not sigma. I have to write whole function from here to here, and after that I have to write whole function for sigma minus like this. Okay, so I have to take derivative with respect to sigma. So I have taken derivative with respect to this, and after that multiplying with this. So this and this is going to so from chain rule, and after that what happens, I have Jacobian function. So dou f by dou x is Jacobian function, but in place of x now I have this whole quantity. So due to that reason function is going to become change, and after that y minus x, because dou x and dou not x plus sigma y minus x, and if you take derivative with respect to sigma, so this is 0 and this is y minus x. So due to that reason this comes into picture. Anyone has confusion on this? Vinay? Vinay, are you here? Okay. Okay, so if this is clear, now what I am going to just 5 minutes I will complete within 5 minutes. So what happens? Now what I am going to do, somehow I have to establish the multi-dimensional version of mean value theorem. So again fy minus fx, and you can see that whenever I am writing fy minus fx, So if I am going to substitute h1, then I will generate fy, h0, then I can generate fx, and after that you can see from here I have defined this function, and I have already discussed this point. If sigma equal to 0, then I am at fx, and if sigma equal to 1, then I am at y. So I am able to write like this also. So if I have this kind of quantity, so by the property of definite integral, I can able to write like this. Suppose you have some quantity, so derivative is the inverse process of the integral. So same kind of things I have used here, then I can generate. Now what I have done, after writing this, I have just substituted this kind of quantity from here, and I can finally come up with the mean value theorem. And due to that reason, we have defined mean value theorem like this. Anyone has confusion? Okay, now let us come that how to apply mean value theorem. So you can see here that in order to approximate something, I have to apply, or I have to assume that Jacobian matrix exists. And due to that reason, what I am going to do, I am assuming that this function f is infinite many times continuously differentiable. And since linearization technique is only valid in very small region, and due to that region I have created some kind of ball. What is meaning of this double symbol? Suppose that if you have x1, x2 up to xn, so we are talking about norm. So one of the simple norm is two norm. Two norm you have already know that what is meaning of two norm: x1 square, x2 square, x3 square, and less than r, because this is now whenever you are going to calculate talk about norm, then n dimensional quantity is converted into one dimension. So this will create some kind of ball. I will discuss about this point again, because norm and these kind of things I haven't discussed till now. So what I am telling, that in order to apply this kind of linearization, first you have to confirm that your function is continuously differentiable infinite many times, and after that, that is only valid in some approximity, that is d, and radius equal to 0, greater than 0 means very a small vicinity of the equilibrium point or that point. And after that we are also assuming that f0 equal to 0, because without loss of generality I am assuming that 0 is the equilibrium point. Now what you can do, you can apply the Jacobian here. Jx I have defined like this, dou f by dou x. Again, whenever we are writing like this, it means that we are talking about this dou f by dou x into x minus 0. Okay, now since f0 equal to 0, so what I am going to do in that mean value theorem, this theorem, in place of x I am going to substitute 0. So if you substitute 0, you can see here dou f by dou x, and here x equal to 0, and after that sigma y and d, and after that this quantity becomes 0. So similar way, you can see here that if you substitute y equal to 0 or x equal to 0, that doesn't matter, then I will get this kind of approximation, that fx equal to this. Here you can see that I have written equality sign. Why I am writing equality sign? I haven't done any kind of approximation till now. Okay, and due to that reason, what now I am going to do, I am going to add and subtract the Jacobian matrix from this. So basically I have defined this as a gx as a some kind of quantity, whatever quantity I have received from here, and after that I am going to substitute Jacobian about the origin. So Jacobian about the origin a equal to 0, and in this way I can generate this, and gx I am going to generate this function minus Jacobian of that. So in this way, in concrete way, I can able to write fx equal to, not approximated, equal to this. Okay, and it is possible to show, since fx is continuous about the 0. So if you are going to do approximation about the 0, then this term equal to 0, gx tending toward 0, and due to that reason my function fx is approximated by a into x, like this. So now whenever you are going to write some kind of paper in control system, at that time you please do not apply the Taylor series approximation. You have to go via this way, and due to that reason I have taught, because most of you are the student of PhD or master. Okay, so please, what you can what is main thing, that whenever you are writing approximation of something, so mathematically it doesn't look that where that is valid, but here if you write up to here, you can see that I haven't done any kind of approximation till now. Here up to here I am right talking about equality, and after that now you can analyze the gx term, and then you can impose something else. Okay, so when I will discuss about continuity, at that time I will tell you that why x tending towards 0, then gx tending towards 0, and fx is approximated by ax. Okay, so sorry for little bit longer class, but what we have seen in today's lecture, that I have started with the the nonlinear system, and after that we try to understand what is meaning of Taylor series in different way, and how basically linear algebra will generate some kind of, or generate some kind of relation with calculus. And after that second interpretation, what we have seen, that I have some small neighborhood, and due to that reason by concept of derivative I can generate, by concept of derivative also I can generate the coefficient of Taylor series. Okay, and finally I have used that kind of analysis to see the qualitative behavior of nonlinear system in vicinity of the equilibrium point. Okay, and finally I have talked about the multi-dimensional mean value theorem and its application for the linearization. So with this remark, I am going to end the today's lecture. Now session is open for the questions. So if you have any question, then please let me know. Anyone? Okay.